This tutorial is part 2 of a 4-part series that covers designing and using cost structures in your agreements. In this tutorial, we'll show you how to design cost structures. This is an advanced topic that is aimed at senior sourcing professionals who are responsible for implementing their organization's sourcing strategy in collaboration with suppliers. If you are a cost structure user, such as a buyer or supplier, we recommend that you check out our tutorial on product management, which is the next topic in this series. In order to follow along, you'll need to be really comfortable with attributes and resources. If this is not the case, then please complete those tutorials first before continuing. Here's what we'll cover in this session. First, I'll do a deep dive into the building blocks of the cost structure, the cost item. I'll explain how their properties influence the way that they are implemented in the products and spend some time on formulas and their attributes. Then we'll look at the bigger picture and explore the process of rolling up the cost structure using each cost item's formula. I'll explain the role that dimensional analysis plays in determining the unit of measure of the individual cost items and, ultimately, the units for the selling prices of the products in the agreement. With the theory out of the way, Natasha will demonstrate what we just learned by building the cost structure for a fictional sheet metal fabrication agreement. Right, let's get started. The building block of a cost structure is the cost item, which represents a discrete unit of cost. It could be a material, an operation, or an entire process. A cost item really only has one job: to define how it should be implemented as a product cost item. You control how this happens by defining its relationship to the other cost items in the cost structure and by setting its properties. Let's talk about relationships first. Each cost item may have a single parent and any number of children. This hierarchical relationship between cost items is where the true power of cost structures comes into play. You can model even the most complex commodities by using these apparently simple building blocks. Each cost item has several properties which affect how it's implemented in the product costs. The name and description of the cost item are self-explanatory. They are automatically copied to the product cost item when implemented, but they can be changed thereafter. The name must be unique within its siblings, but the description is optional and does not need to be unique. The three most significant properties of a cost item are its mandatory and repeatable properties and its formula. The first two properties influence the behavior of the cost item when it's implemented, and the formula determines how its value should be calculated when it is a product cost item. To show you how you might use the mandatory property, suppose you have a cost structure containing a packaging cost item with the child carton. Let's say this cost structure is implemented in two products. The bike has packaging, but the motorcycle doesn't. If you want all products with packaging to use a carton, then you check the carton's mandatory property. Those products with packaging would automatically implement the carton, but those without packaging wouldn't. When a mandatory cost item is implemented in the product costs, it can't be removed unless you uncheck its mandatory property. Unchecking its mandatory property does not automatically remove it. The second property that I want to explain is the cost item's repeatable property. This setting is useful when you want to model a repeating material or operation in your cost structure. Again, the best way to explain is with an example. Suppose your cost structure models a painting process and you've defined a cost item called paint layer. Let's say our bicycle product is added to the agreement and the painting cost item is implemented. By default, only one layer can be added to the painting cost item. But when you check the layer's repeatable property, you can repeat it multiple times. Conversely, unchecking the repeatable property forces Mercenter to automatically remove the repeated instances. Now let's talk about the most complicated property of cost items, their formulas. Every cost item must have a formula which determines how its value or cost will be calculated when it's implemented as a product cost item. A formula consists of a list of formula items, each containing a math operator and an attribute. Currently, we support 4 operators: addition, subtraction, multiplication, and division. We can add more if required, but so far we haven't needed to. The principle here is that each cost item should be simple. Complexity for your model can be built using cost structure hierarchy, as you'll see later. The first formula item must be a plus, but the others can be any math operator. We currently don't yet support brackets, so you'll have to expand algebraic formulas first if they contain brackets. For example, suppose you have the formula a times b minus c in brackets, then you'll need to first expand to a times b minus a times c. When Mercenter executes the formula, it does not run the calculation strictly sequentially. We follow the mathematical order of operations which you may remember from school as BODMAS. Under these rules, multiplication and division are done first, then addition and subtraction. So for the calculation 1 plus 2 times 3, we first multiply 2 and 3 and then add the result to 1, producing 7 as the result. You can use any number type attribute from within the agreement anywhere in your formulas, except for product cost item attributes which have some special rules that you'll need to know about. This attribute comes in two forms. Let's talk about each one in turn, starting with the one you're most familiar with. You can create custom properties just like any other attribute. These attributes are extremely useful, and you'll use them a lot because they allow you to define custom properties which are unique to each product cost item, even when they are repeated. Unlike other attributes, however, they can only be used in two places, either in the formulas of the current cost item or in those of its immediate parent. Continuing the painting example we mentioned earlier, suppose you define a coding weight attribute. You could use this attribute in the formula of its own cost item or in the parent or both, but nowhere else. If you repeated this cost item in the product costs, then you could set the undercoat to 100 and the top coat to 150 grams per square meter, independently of each other. The second form of this attribute is called the formula result, which predictably represents the result of the cost item's formula. This attribute is created for you automatically by Mercenter when you create a new cost item and is not editable by users. The system updates its unit of measure and value for you automatically whenever it rolls up the agreement's cost structure. More on that later. You must use it in the formula of its immediate parent. There are no rules about how it can be used. I'm showing them being added, but in fact you can use them however you want. This is the mechanism which Mercenter uses to connect a child cost item to its parent. Because this attribute is the result of the cost item's formula, it can't be used in its own formula, otherwise you'd get a circular reference. Don't worry about making mistakes because Mercenter simplifies it for you by hiding options in the user interface, making it easier for you to create formulas which comply with these rules. Whenever you make a change to a cost item or any entity that it depends on, Mercenter recalculates or rolls up the cost structure. When we do this, we calculate the units of measure for all the cost items, starting from the bottom, working upwards until we reach the top level. The top level cost items are those without parents. What we're really doing, behind the scenes, is updating the unit of measure of the formula result attribute for each cost item we talked about before. Mercenter uses a mathematical technique known as dimensional analysis to calculate the units of a cost item using its formula. We do this to help identify any errors or inconsistencies in your formulas and to calculate the units for cost items and ultimately the units for the selling prices of the products. The technique allows you to cancel out equivalent units when you're multiplying or dividing attributes to produce new units. Notice in the example on the right that the units of kilograms get cancelled out, resulting in a new unit, dollars per each, that's different from either of the original units used. You can only add or subtract units if they are exactly the same. This is a useful check for your formula to make sure you are adding or subtracting apples from apples, so to speak. Remember also that the same rule applies to dimensionless units. Because dimensional analysis is used in our cost structures, you'll need to be very precise with the units for your attributes. Units in Mercenter are case sensitive, so kilogram and kilogram with uppercase K aren't equivalent. To illustrate how it works, consider the formula used for calculating the resin cost for injection molding. You can see here that we're multiplying the shot weight attribute in grams by the attribute for the price of the resin in dollars per kilogram, then dividing by the attribute for the cavity count in each per cycle. I've extracted the units on my scratchpad so you can see how dimensional analysis works behind the scenes. First, I'm going to invert the units for the cavity count attribute and change the operator to multiply, allowing us to see what's going on. In this case, we can only cancel out the cycle unit, which results in the nonsensical unit you see. That's because the weight units can't be cancelled. When this happens, you'll know that you need to add a conversion attribute to convert from grams to kilograms. When we do that, you can see that the kilogram and gram units cancel out, producing dollars per each, which is exactly what we want here. If any errors occur during Rollup, the dimensional analysis will stop, and the cost item where the error occurred, along with any cost items higher up in the hierarchy, will be invalidated. This makes it easy to see where the error occurred for troubleshooting. If the cost structure is invalid, then by extension, all product costs are also invalid, and you won't be able to submit the proposal for approval when in this state. On the other hand, if the Rollup reaches the top level without errors, and all the top-level cost items have the same unit of measure, then the Rollup was successful. The result at this point is the unit of measure of the selling prices of all the products in the agreement. Macenta requires the top-level unit of measure to be the same because it adds the top-level product cost items to calculate the final price. But I'm getting ahead of myself, we'll cover that in more detail later. That's pretty much all you need to know about cost structures at this stage. I'll hand you over to my colleague, Natasha, to demonstrate what we just learned.
Thanks, William. For this demonstration, I'm going to show you how to build a cost structure for a sheet metal fabrication agreement. I selected sheet metal because its cost structure is quite complicated, as you'll soon see, so it allows me to demonstrate some of the more advanced features. Don't worry if you don't have any experience with sheet metal stamping. I'll give you a quick primer now, so you'll understand just enough to know what's going on when we build the cost structure later. The main raw material used in stamping is sheet metal, usually in the form of galvanized steel, but mild steel, stainless, and aluminium are also quite common. The sheet could be supplied as cut sheet or coil, but this depends on the capability of the machine and the die design. In most cases, only a single sheet is used to produce a finished product, but it's possible that many types of sheet could be combined through a process known as clinching, which we'll need to factor into our cost structure. Another area that we'll have to consider in our cost structure is scrap. Stamping often generates large amounts of design scrap, which we call offcut or trim. Fortunately, this scrap is valuable and can either be reused as a byproduct for other parts, or sold to scrap dealers to offset the cost of the part. The dies used in stamping are typically made of hardened steel, and are used to shape and cut the sheet metal during stamping. There are many types of operations that a die could perform, including blanking, piercing, bending and forming, among others. Producing a finished part from flat sheet usually requires multiple stamping steps using different dies to achieve the desired shape. In most cases, this is done by transferring the semi-finished parts from die to die, often on different machines either manually or robotically. This is called transfer stamping. There are also progressive tools, but I won't get into that now. Like dies, the stamping machines used to form the part are another hugely complex area, which I won't go into with a lot of detail. Fortunately for us, pricing is usually quite simple. It's usually quoted in price per stroke. The key determining factors of the price are the motive power of the machine and its maximum force. Okay, so now you're an expert on sheet metal fabrication. Let's log in and start working on the agreement. For this demonstration, I registered a fictional organization called Neptune, with a single manufacturing site located in Mexico. The subdomain that I will be using to access our portal is at neptune.macenta.com. Yours will be different, of course. I signed into the portal and landed on our homepage. For this demo, I'm using version 1 of the software. We've recently been making a lot of changes, so your portal might look a little different. I'll update the tutorial if the changes are anything more than aesthetic. To prepare, I created a proposal for a new agreement with a fictional supplier, Acme. To view this proposal, click Agreements on the main menu, and then when the Agreements menu loads, click the proposal titled Sheet Metal Fabrication in the Acme Counterparty section. Before we dive into cost structures, let's take a look around to show you what I've done. First, notice that I've created 3 agreement attributes that we'll be using later in our formulas. The first 2 are just conversions between hours and seconds and kilostrokes and strokes. They will come in handy later when we adjust the units of measure in our formulas. The last attribute is the most noteworthy. It represents the price that the supplier has quoted for stamping the parts in dollars per thousand strokes per ton. This method of pricing is quite common when the parties want to keep pricing simple and the supplier's machines are of a similar type and cover a small range of sizes, which is the case for this agreement. Our supplier is only providing pneumatic and mechanical machines over a 20 to 75 ton range. Next, let's take a look at the resources which I created earlier. Click the Resources menu item in the Agreement section. When the menu loads, you can see that I've created several resources. Let's look at each of these in turn without going into too much detail. Click the Tool resource first. This resource represents the dies or tools used to press the parts. When the menu loads, you'll notice that this resource has 3 attributes. First, the cavity count represents the number of pieces that will be produced for each cycle of the die. The second attribute, gross weight, represents the weight of the sheet metal that will be fed into the die. The third attribute, offcut, is the design scrap I mentioned earlier. We'll use these 2 later to calculate the net weight by just subtracting the gross weight from the offcut. Also note in the Items section that I added a few transfer dies, which we'll be using later when we configure a product. Let's move on. Next, the sheet resource represents the metal sheet from which the metal parts will be created. The attribute that we'll be using in our formulas is the price in dollars per kilogram. In a real agreement, you'd want to specify a few more attributes like the grade and type of metal, but I'm limiting the attributes to the bare minimum you'd need to build our cost structure. Notice again at the bottom that I've added a couple of cut sheets that we'll be using later. The next resource, stamping machine, represents the machines that the supplier will make available under the terms of this agreement to press the parts. The solitary attribute you see here is the force, which represents the size of the stamping machine. When we build the formula later, we'll multiply this number by the machine rate you saw earlier to get the fabrication price in dollars per stroke. You can also see here the 25-ton pneumatic and 50 and 75-ton mechanical machines in the supplier's inventory that the supplier has made available for us. Next, the degreasing machine resource represents the degreasing process used to remove lubrication oil from the parts. The only attribute here is the price in dollars per hour. Next, the recovery scrap resource represents the recovery scrap generated from offcuts and other trim which the supplier will sell to offset against the sheet price. The only attribute here is the price in dollars per kilogram. I've also added 3 types of scrap, each with a different selling price. Finally, the labor resource represents any assembly or specialized labor which will be provided by the supplier to handle any labor-intensive work, such as assembly or welding. The only attribute here is the rate in dollars per hour. Okay, that's the resources covered. Now let's take a look at the cost structure. In the same proposal menu, click Cost Structure in the Agreement section. When the Cost Structure menu loads, you'll notice that we haven't defined anything for this agreement yet. We'll do that shortly, but before we jump in, let's choose the best way to design it. The way I see it is that there are 2 ways to model the transfer steps, either horizontal or vertical. Let's look at each of these ways before we decide. Each method leverages either the mandatory or repeatable features of cost items, and has its drawbacks. The horizontal method exploits a feature that allows cost items to be repeatable. If we use this method, we'd have a cost item representing a step and set it to repeatable. Then when we implement this cost structure in the product, we could just repeat it for each stamping step. Sounds simple so far, but the problem is that each step produces a different number of parts on account of its cavities. To handle that in the formulas, the cost of stamping the product would be the formula result for step N divided by the total quantity of products produced as a product cost attribute. When this is implemented, the configurer would need to calculate and input this quantity so Macenta can calculate the total stamping cost as I've shown here. Another option would be to push the calculation down to the cost item. Then the quantity would be a product cost item attribute, which the configurer would calculate as the number of products produced for each step, but that's even more confusing. Both methods require the configurer to do calculations outside Macenta, which is error-prone and difficult to audit. On the other hand, if we used a vertical method, we'd pre-build a hierarchy of steps, starting from the final step and working backwards, adding a child for each upstream step. This method exploits a feature of cost items that allows them to be optional in the product costs. If we didn't need a step, we just wouldn't implement it. The disadvantage of this method is that the number of steps would be finite, which turns out not to be a problem, because I can't imagine a part needing more than about 5 steps. And we could also add more depth if needed after we go live. The advantage of this method is that we wouldn't require the product configurers to calculate the number of parts produced because the cost of the parent would just be the cost of the upstream step. Actually, it's a little more complicated than that, as you'll soon see, but you get my drift. Another advantage of this method is that if we needed clinching, we could just introduce the sheet at the step where it's needed. It's clear that the second method is the way to go. The setup is more complicated for the designer, but it's much easier for the product configurer. What I'll do is first create the entire hierarchy of cost items so you'll get a bird's eye view, and then I'll circle back and wire up the formulas. In fact, this is a good way to go because the formulas of a parent cost item will depend on the formula results of their children. For this agreement, there will be only one top-level cost item, representing the total cost of the stamped part. In a real agreement, you'd probably need cost items for surface treatment, logistics and packaging, and so on. To create our only top-level cost item, click the plus icon to the right of the Cost Structure section and enter a name. Like all names in Macenta, they are limited to 50 characters and must be unique amongst its siblings. Notice that I'm leaving the parent empty, indicating that this cost item doesn't have any parents. Then click the Save button. When the cost item is created, Macenta will automatically open its menu for further actions and configuration. Before we set its properties, let's take a look around. The Actions section allows you to reorder the cost item up and down amongst its siblings. The Remove button will remove this cost item along with its children. These actions are self-explanatory, so I won't demo them this time, because we've got a lot to cover. The Configuration section allows us to set the cost item's properties and formula. Finally, the all-important Product Cost Item Attributes section is located at the bottom of the menu. For now, I'll set its properties. I'll click the Properties menu item, and then when the form loads, I'll input a description for the cost item. Each stamped product must have a stamping cost item, so I'll check its mandatory property. I'll leave its repeatable field unchecked because there should be only one for each product. Then I'll save my changes and close the form. Now let's add the first stamping step. Click the plus icon again and name it Step N, indicating that this is the final stamping step in the part production process. For example, in the product costs, if there are 3 steps in total, then we'd name this Step 3. The parent will be the stamping cost item we just created. When it's created, I'll navigate to its properties to input a helpful description. And then I'll check both the repeatable and mandatory checkboxes. We want to be able to repeat this if there is more than one stamped part to be assembled. Now let's create a cost item representing the sheet metal, which may be used by this final step. Click the plus icon once more, and type in sheet N, indicating that this is the sheet used by the final stamping step, step N. When it's created, I'll type in a description. I'll leave the mandatory checkbox unchecked because step N may just use the semi-finished output from the previous step, which I haven't yet created. Or this step might use both if we're clinching. I'll check the repeatable checkbox to allow multiple sheets to be used. Since this step is the final one, we may need to clean it before it's welded or assembled, or sent to the customer. So I'll create a degrees cost item. I'll leave both the mandatory and repeatable properties unchecked. Now let's create the upstream step. I'll name it step N-1, indicating that this step comes before step N. I'll leave this step optional, but I'll allow it to be repeated in case we're clinching together multiple parts. I'm moving quickly now because you've seen me do this before. The next thing I'll do is create 3 upstream stamping steps, step N-1 and step N-2. These will mirror what we just did with step N, except that degreasing won't be required. Each step will provide semi-finished parts to its parent, up to the top level. In a real agreement, you'd probably need about 5, just to be sure, but for this demo I'll just allow 3 steps. Finally, I'll create an assembly cost item, which represents any additional work required, like welding or fastening the parts produced from the repeatable step N. Once it's created, I'll key in a description. There, done. Let's review how it works. The idea here is that if a part requires all 3 steps, then we'd first stamp the part on step N-2 using sheet N-2. The output of this step, along with optional sheet N-1, is consumed by step N-1. These 2 steps are optional, so if we don't implement them, then they won't be used in the formula for the parent. Then the output from step N-1, along with sheet N, would be consumed by step N if they are implemented, and so on. Now that the overall structure is complete, we'll do the hard part, creating the formula for each cost item, starting from the bottom and working upwards. At the same time, I'll also define any product cost item attributes that we need in the formulas. You'll know if your cost structure has errors in the formulas because there is a sea of red warnings in the cost structure menu. Another indication of problems is that the unit of measures are missing from each cost item. Click the bottom cost item, sheet N-2. When the form loads, I'll define a new attribute called material loss allowance, which is where we'll allow the supplier to account for any uncontrollable material losses incurred during the stamping operation. Because you should already be familiar with attributes, I won't dwell too much here. This attribute is dimensionless, so a value of 1 represents no losses, whereas a value of 1.1 means 10% more material was consumed than the design quantity. I've set the minimum to 1 and a default value of 2% loss. This attribute will actually be used by the parent. You may remember that we allow product cost item attributes to be used by the immediate parent of the cost item. Now let's create the formula. Click the Formula menu item in the Configuration section of the Cost Item menu. When the form loads, you'll see the formula is empty. The value of this cost item is simply the purchase price of the sheet, so there is not much to do here. Click the plus icon and select the price attribute of the sheet resource, then click the Add button to add it to the formula. Once the formula item is created, you'll notice that new items are added with the plus math operator automatically, which happens to be what I want. You may be wondering why we didn't just use this sheet price in the parent. We could have, but remember the sheet is optional, so defining the price in a cost item and making it non-mandatory allows us to toggle it on and off in the parent. Next, we'll work on the total cost of the first step. Click the step N-2 cost item, which is the parent of this sheet. For this cost item, I'm going to define two product cost item attributes, one representing a productivity loss factor, which will allow the supplier to account for any uncontrollable inefficiencies in stamping the part. This is quite common in supply agreements. We could have specified this at the tool level, but it makes more sense here since its value really depends on the interaction between the tool, machine and material. Second, I'm going to define an attribute for the quantity of this part, which will be consumed by the next step, step N-1. In most cases only one piece will be used, so I'll set its default value to 1. Now that we are done with the attributes, I'll build the formula, which is a lot more complicated this time. When we load the formula form, you'll notice that Macenta has automatically added the formula result for sheet N-1 to the formula. Macenta does this automatically to prevent orphans. The value of this cost item is the net material cost plus the fabrication cost. The net material cost is the gross cost minus sales of the offcut, which I'll call recovery. The gross cost is the sheet price times the gross weight, and the recovery is the offcut weight times the scrap price. Don't worry too much about the math here, it's not important for the tutorial. What I want you to understand is how I'm building the formula using various attributes from the agreement. Let's do the gross cost first. I'll leave the first formula item alone and multiply it by the gross weight from the tool. Then I'll multiply again by the material loss allowance, a product cost item attribute from the upstream cost item. Then divide by the number of cavities, also from the tool. That's the first segment done. Notice that Macenta automatically calculates the resulting units of this formula as dollars per piece using dimensional analysis. Also notice that Macenta displays this same unit in the cost structure menu. But we are not done yet. Let's subtract the scrap recovery from the gross cost. The calculation is the offcut weight, which comes from the tool, times the scrap sale price, from the scrap resource, divided by the number of cavities to get the recovery per piece. I'm moving a little faster now, because you've seen me do this already. The final segment is the fabrication cost for this step. The formula for the fabrication cost is the machine rate, times conversion from kilo strokes to strokes, both agreement attributes, times the fabrication loss allowance, times the machine size, divided by the number of cavities. Before we move on, let's review what we've done. There are 3 segments here. The first segment is the sheet calculation, which uses the material loss allowance from the sheet cost item, as well as resource item attributes from the tool. Then in the second segment, we subtract the scrap recovery, which uses the scrap recovery price. Then the third segment adds the fabrication cost. At the bottom, Macenta has calculated that the unit of measure of this cost item is dollars per piece, which is a good indication, but not a guarantee of course that we are on the right track. Let's move up one level. First let's do the formula for the sheet N-1 cost item, which will require the same material loss allowance attribute. This is almost exactly the same as what you saw me do before. I don't want to be repetitive, so I'm going a lot faster now. Then the formula for the sheet Then I'll build the formula for the step N-1 cost item. First I'll define the same productivity and quantity attributes you saw me do before. Then the formula, which is exactly the same, except I'm going to add one more segment, which I'll show you when I'm done. Okay, that's the formula complete. Let's review what I did. This time the formula has 4 segments rather than 3. The difference here is the third segment, which takes the formula result for the previous step and multiplies it by the quantity. That quantity is a product cost item attribute from the child. Okay, let's keep going, we are almost done. The last stamping step, step N, has 3 child cost items: the sheet, the semi-finished product from the previous process, and a degreasing cost. First I'll do the formula for sheet N. This is identical to all the other sheets. We use the same material loss factor attribute, and the formula consists of only one formula item using the purchase price. Next I'll do the formula for the degreasing. First I'll add an attribute representing the degreasing speed in pieces processed per hour. This is a product cost item attribute, because the speed depends on the surface area of the part produced by this step. Now, let's build the formula. The cost of degreasing is quite simple, just the machine rate, from the degreasing resource, times the speed, which you just saw me define a second ago. Now that the degreasing is done, we are ready to do the formula for the last step, step N. First I'll define an attribute for the productivity, as we did before. Next I'll define an attribute for the quantity, but this time the unit of measure is pieces per each, which is different from the pieces per stroke that we used before. This attribute represents the number of pieces to be assembled into the final product. In mathematical terms, we are simply converting the unit of measure from pieces to each. In most cases this will be 1 piece per each, so I've set the default value to 1. You can see how Macenta forces you to be very precise with your units. Right, let's build the formula. This one is a little more complicated because we need to add segments for the degreasing and also add the new quantity attribute in each segment. Phew, that was a lot of work. The good thing is that you only have to define the cost structure once for your agreement. This time we have 5 segments. The extra segment is the addition of degreasing. Notice that each segment multiplies by the quantity from this step so that the unit of measure of this cost item is dollars per each. Other than that, it's the same as the previous step. Now that we've done the stamping, we need to do the cost item for the assembly of the stamped parts. But before we do the formula, I'll need to add a product cost item attribute called cycle time, which represents the time in seconds to assemble the parts produced by the stamping operations. The cost of assembly is the hourly rate attribute from the labor resource times the cycle time, which you just saw me define, divided by the conversion from hours to seconds, which is an agreement attribute. Finally, we need to build the formula for the top-level cost item, which is stamping. This item's formula should add the cost of the stamped parts and assembly. Fortunately, as you can see, Macenta has already set up this formula for us because they are child cost items and these are added by default, so we don't need to do anything else. Notice that the final unit of measure of the cost structure is dollars per each, which corresponds to the unit of the selling prices for the agreement. On that note, I've come to the end of the first demo, so I'll hand you back to William for more theory. I'll see you soon for the second tutorial, where I'll use the cost structure we just built to configure the products. See you soon.
Thanks, Natasha. With that last demo, we've reached the end of this tutorial. Thank you for your attention and congratulations for staying until the end. Before you sign off, I'd like to give you a quick recap of the topics we covered. To begin, I delved into the building blocks of cost structures, the cost item. We explored how cost items can be used to model even the most complex commodities by leveraging their hierarchical, repeatable, and mandatory properties and formula. Although you are already familiar with attributes in general, you may not have realized the essential and powerful role that product cost item attributes play within cost structures. I explained how the formula result plays a vital role in establishing the hierarchical form of cost structures by serving as a crucial connection between a cost item and its parent. Additionally, because these attributes can be used in their own formulas as well as in those of its parent, their true power is evident when a cost item is repeated, producing a multiplicative effect on the generated formula, which you can use in commodities that require this feature. Finally, we covered cost structure Rollup. I emphasized the important role that dimensional analysis plays in determining the unit of measure of a cost item and how its formula is used to calculate the value of the cost item when it's implemented in a product cost. We certainly covered a lot of material, but by now you should be well equipped to effectively design cost structures for your agreements. Goodbye.